Ba-da-da, spring, spring, spring. Okay, so we've been talking about forces with F equals ma. We've talked about like tension forces, pushing forces, like compressions. We've talked about friction on some of our last videos. And one kind of different force that we need to talk about is what's known as a spring or an elastic force. Okay. Most springs follow a linear relationship referred to as Hooke's law. And that's Hooke with an E because, spelling names is complicated, right? So Hooke's law essentially states the following. If you have a spring, the force from a spring is going to equal negative, which is kind of a weird thing, but we'll talk about that. It's going to be a negative, and then it's going to be a K and then an X. And what these two variables represent are the K is a spring constant. It reflects the strength of the spring, okay? So this is like the strength of the spring right here. If you think about springs that you may have seen in the past, some of them can be pretty small, and you can just kind of, push them in or pull them with your finger. Case in point, we've all had pen races at some point in time. There's a little spring on the inside of that pen that allows you to depress it and pull it out. That's a very small spring. There are very, very large springs on your cars, if you want your shocks or anything like that, or like rally racing or something. Those are very, very strong springs there. They're very, very thick. They're very hard to compress. It takes thousands of newtons of force to compress some of them. And it's entirely based off of what is your spring made out of. Is it made out of paper? Is it made out of aluminum? Is it made out of like a steel material? Or what is the thickness of that spring? Is it very, very thin? Is it very, very thick? Like, how did you physically build it? So the spring constant is entirely just based off of the physical properties of your spring whenever you forged it in the fires of Mordor. Whatever. Okay. The second thing that we talk about in terms of the spring force, which is a vector, is the displacement. This x here, we sometimes write as a delta x earlier in the year for a displacement, but here we're just writing it as an x because with springs, that's what we're thinking about. And when we think about a displacement for the spring, we're really talking about an extension, like a stretching of the spring, or a compression of the spring. And it's how far you've stretched or compressed the spring from its equilibrium position. And what do we mean by an equilibrium or equilibrium position? Well, that's kind of like the rest position of the spring. So let's jump over to the lab real quick and actually take a gander of like what some of this will look like here. And if the audio is a little low, you may have to turn this up the way my mic's set up. But let's jump over to the lab and check this out. So to the lab. Pew. A hawk. Okay, so what we're looking at here, hanging from a spring, is, so we've got a mass here at the bottom, and this is a spring sitting right here. So right now, this spring is in a rest position. It is technically in an equilibrium position right now because the weight from the mass, pulling it down, is being acted in an opposite direction by an equal force, the spring pulling it up. So this technically is an equilibrium position right here. If I pull this a little bit further and I let go, you might have an idea what's going to happen. It pulls back up and starts going back and forth. So when I pull a little bit further, this spring is being stretched and there is a spring force here. Okay? Now, technically speaking, there is a spring force here. That's the spring force that is being equaled by the weight pulling down. If I undid this mass and I let it go back up, the spring would be rest up here. This spring, though, the way it was built only to extend, so I can only stretch it, okay? But as I stretch it more and more and more, there's more spring force in that spring. And you may have experienced this with something like a rubber band. If you've ever tried to snap a rubber band onto someone's skin, a common thing we did in middle school, the more you pull it back, the more it's going to hurt in a second. So, as you extend the spring more, there's more and more force behind it. And that same idea applies with a compression. If you try to compress something, it's going to push back more and more and more, and it has more force behind it. But this is technically an equilibrium position we always think about our spring forces as being based around an equilibrium position. Whether that is previously stretched, so even though there is a force in this spring, if you want to think about it from this point, it is nice to just think about from here, how much more did we stretch it? So like from here to here, that little stretching distance is important to think about. Or how much did we compress it to move it up? Okay, so those are things that we think about for springs. And if I put a different mass on this spring, so here's a smaller mass. What I had previously was 500 grams. This is only 200. We'll see that the spring doesn't stretch as much because there's less weight on it. So there's going to be less of a spring force here to equal that out. But the spring constant is still the same. The spring constant of a spring was determined when this spring was created many, many years ago, and that will not change. The only way you can actually change a spring constant is if you actually try to destroy a spring. If you were to take this spring here and if you overstretch it, you really, really stretch it so it kind of warps the metal, at that point you'll have changed the spring constant in some way and kind of messed up the spring. Or if you melt it down, right? So it becomes nothing. But in general, that spring constant is what it is. It's not going to change. And the only feature that really changes on a spring whenever you're using it is how far you stretch it. So let's take it back into our notes and take a look at some of the things that we can do with these springs, how we can think about them in new ways, and what's going on there. So, okay, so we're looking at our notes here, and we've got the idea of the strength of the spring and the compression or the extension. So if we move on from this, this equation, this Hooke's law, F equals minus kx, it's going to work with most springs, okay? But technically not all. Whenever you say all, that's a really important word, it works for everything then. Technically some springs actually obey a similar law, but they're minus x squared. So there's a square term in here for some things, okay? Also, this Hooke's law, this minus kx, it also works for some things that aren't springs, like rubber bands in some cases, or bouncy balls. So, if you drop a super ball or a rubber ball, sometimes it works for that too, okay? But in the end, this spring force is just a force. Now, one of the weird things that always throws people for a bit of a loop is why is there a negative in the equation? The spring force equation is minus kx. And the reason there's a minus here is because a spring force is what is known as a restoring force. It is a restoring force. And what we mean here by that is the following. Imagine I have a wall, and here's the ground. And on that wall, I hook up a spring. Okay, so here's a spring. And at the end of the spring, I put a block. Okay, and this is the equilibrium position of the spring. And this is the center of the block right here. If I call the right direction positive and the left direction negative, because we need to pick positive and negative directions, that's a thing we do, right? If I stretch the spring, if I pull the spring to the right, my x value here is going to be positive because that's the direction I stretched the spring. I stretched it in the positive direction. Well, if I stretch this spring, what direction does the spring itself want to act on the block? Well, the spring wants to do the opposite of that. If you pull the spring to the right and you let it go, it's going to snap the block back to the left. So in this case, the spring force will act to the left and it will be negative. It is the opposite of the displacement. Likewise, if you compressed this spring to the right with a negative, then the spring wants to push back, or if you compress the spring to the left, negative, the spring wants to push back to the right, which is clearly positive. So it's the opposite of the negative, it is positive. So this negative here, it really just designates what direction is the spring pushing. Most of the time, whenever we do problems, because we are always drawing good free body diagrams, we really don't even need to think about this negative value here. We just need to ask ourselves, what direction is the spring force acting? And then just use our positive and negative directions to get things to work out appropriately. Okay, so if you don't like using that negative up in the equation, just think about it as, where does this spring want to push or pull? Is that direction positive or negative? And just do things like we've normally done in our free body diagrams and our F equals ma equations in the past in order to set them up appropriately. Okay, so let's take a look at how we can apply this F equals kx equation, or negative kx if you'd like, to kind of a problem or a setup here. So what we have is a very similar picture to what we just set up in the lab. We have a spring with a block hanging from it. And technically the block is attached to a rope here, but the rope, we might as well just say like the block is directly attached to the spring. Nothing's going to really happen there. But the block is stationary here, okay? The block is stationary, so it's not accelerating at all, okay? The acceleration is 0. We're asked to determine the tension in the rope, which is really going to be the tension in the spring force, and the position of the end of the spring relative to its rest point. So let's, we've kind of got a picture here. And if we kind of imagine it, what we have here is some ceiling up here, and there was once a spring tightly bound, but then that spring, when a block got attached to it, it stretched out a little bit, okay? And if we were to draw the free body diagram on this, what we'd have is a block, and I'll draw it in red. So here's our block. And that block has a weight on it. We see that weight is mg, 98 newtons of force. With a little bit of quick math, we can see that the mass of that must be 10 kilograms. And we'll see that in a second. So our weight here is mass times gravity, which is 98 newtons. And there is some force pulling back up on this. Because the block is stationary, we immediately know that the acceleration must be 0 meters per second squared. So there has to be something pulling back up on this here. Technically, it'd be the rope with a tension, but that tension, whatever it is right here, that tension has to be equal to the spring force acting on the inside. So let's just call this pulling back up here. Let's just call it the spring force. Okay, that spring force is what is acting in order to pull everything back up and get it to happen. Because these tensions will, this block attached to the rope is essentially the block attached to the spring. So this is our free body diagram that we have. And I guess if I want to draw it more accurately, this spring vector should be, the exact same length as the weight vector, but, we do our best. Okay, so this is what we have. At this point, if you've been doing a lot of F equals ma problems, you may recognize that, hey, we need to pick a positive and negative direction, and that is really any choice we want to make. So the people have spoken. They want up to be positive, so thus we make up positive. Down will be negative then, it has to be opposite. So if we set up our F equals ma equation, let's do that. We know F equals ma is the sum of the forces, or F net, has to equal a mass multiplied by an acceleration. When we add in our forces here, we have a positive spring force, so we'll call it Fs. And then we have to add a negative weight, so that's like subtraction, right? So minus W. And this has to equal ma. And in our case here, we know the acceleration is 0, so 0 times anything is going to be 0. If it did have an acceleration, we'd have to find that mass by using this equation up here, but in this case we don't. So this is just a 0 because that acceleration was 0. And if we want to go ahead and solve for the spring force here, we can add the weight to the other side. So now we just have a spring force equals the weight, which we know is 98 newtons. And this is why it didn't matter which one was negative, because when we add them over, we just get an answer here. And in this problem, we're actually given the spring constant. And we want to see how much the displacement is. So we're given the spring constant here. It's kind of blurry, but it's 535 Newton meters. And when we recognize that the spring force has to be Kx equals 98 newtons, and I've kind of ignored the negative sign here because I know that this is stretched from its original position. Our K, our spring constant, our strength of the spring being 535 multiplied by X, some stretching distance we're looking for, equals 98. And at this point, we can simply divide each side by 535, and we will find our value of X. And it is, I don't know, some decimal. It's got to be less than 1 here. So 98 divided by 535 is 0.18, and this will be meters because it's how far you've stretched or compressed, if you had that kind of problem, a spring. Okay, so that is one way to go about doing that. Okay, so with that, this problem is finished. Adios. Take it easy.